This video will introduce the logical model and also in part the physical model. So the scope of these models is to go from the conceptual model that we've created previously, which describes the reality, towards a model which describes a database that can be implemented and used. So first I will introduce the logical model and also in part a bit of the physical model. And then we will go through an exercise showing how to transform the conceptual model into a model that can actually be used as basis for a database and implemented in a database. Actually, we will also implement the database. Okay, first a look at the logical model. So the logical model, just like the conceptual model, defines what to store but not how. But there is an important difference, of course, otherwise we wouldn't create a new model, and that is that while the conceptual model describes the reality, the logical model actually describes a data store, but it still describes what to store in that data store, not how to store it. So the logical model is adapted to the type of data storage that is being used, and in this case that is a relational database, but it is not adapted to a particular database management system like Postgres or MySQL. It is still general and can be implemented in any type of relational database. Also, the logical model does not handle physical storage. It does not handle physical things like things that are related to performance optimizations like indexes or security related issues or such things. It is a logical model of a database, we could say. So typical steps taken when going from conceptual to logical model are these. This is not everything that's done, but I'm saying this to define the difference between conceptual and logical model. Okay, one thing is to define which tables to use. In the conceptual model, we were modeling entities, things that exist in the reality, but here we will model tables in a database. And a word of caution here, in relational diagrams, ER diagrams, we often say it is often called relation instead of table. That's the word of the relational model, and in the database it's called a table. And the thing that is called a relation, that is an association between two tables, is called a relationship, which can be a bit confusing. And even more confusing, the two different words for each thing are often used a bit without caution. Sometimes people use the column to the left and sometimes the column to the right. I will try to stick to this column to the right, but I cannot promise never to slip into the column on the left. So we can say that the column to the right is what actually exists in a database, while the column to the left is the relational model. Okay, right, so enough about that. So to decide, in the logical model, we decide which, maybe in the logical model we should call them relations. Okay, never mind, I will say tables. Decide which tables to use, because now we are modeling a database, not the reality. And also to verify that the model is normalized. The logical model as opposed to the conceptual model should be normalized. Also, we should verify that everything the customer has intends to use the database for can actually be performed. For example, the purpose of the visit database that we modeled in our conceptual model exercise was to show which visits were made by which patient to which doctor, for what reason, and at which healthcare establishment. So our database database for that requirement should be able to show this. So we have to verify that everything that the customer wants can be done with the database. Also, the logical model can specify attribute types. but only if it facilitates understanding the data. It's not required to specify attribute types in the logical model, and in particular we should not use DBMS specific database types, like things that are specific for just the Postgres or just MySQL or just some other database type. Okay, so that's basically the most important things of the logical model. It is a model of a database, but it is not enough concrete to be able to make it possible to implement in a database. We still haven't decided on implementation details in the logical model. Right. So then we leave the logical model for a short moment and look at the physical model. So the physical model, as opposed to conceptual and logical models, tells how the data is stored. So now we finally arrive at the actual database, how to store the data, exactly how should the database be designed and implemented. And now, of course, we have to, now that we're actually implementing the database, about to implement the database, we have to adapt it to the specific DBMS, Postgres, for example, that is being used. And also we have to specify all storage details. Now we should really specify the database in complete detail. We have to list all column types, all keys, indexes, and views, and so on. Otherwise we won't be able to implement the database, of course. And also now we must take care of security, which is not part of the logical model. Right, so that's the physical model, an actual model that can be implemented in a database that can be used, that will be the database that will be used. But here in this course we will take a simplified approach, which is very common in the first database course. That is to not create both a logical and a physical model, but substitute them with just one model. And this one model is perhaps often called, at least sometimes called, logical model, and one says that we don't look at the physical model. But that's not really true, because a logical model cannot be implemented in a database, and here we must create something. Since the scope is to actually create a database, we must create a model that can be implemented in a database. So I would rather say that the thing we are creating is a logical model, mainly a logical model. We don't look at implementation details like security or indexes or views or so on. But it has features that belong to a physical model. For example, column types and primary keys, because we're creating something that shall be implemented in a database. Okay, so the conclusion is that our only model is mainly a logical model, but it has sufficient physical detail to enable us to actually create the database. Later in the course, there will be more things related to physical models, like, for example, indexes. So you will later in the course be able to refine the database and take care of more things related to physical model. Okay, so now I will explain how to create our Log-Phys, or rather our logical model with features from the physical model, we can say. And here follows some steps to go from the conceptual model to the model we are creating. But I will not cover them here, but instead, I will not go through them all theoretically, but instead just introduce them step by step, and then we'll actually do each step as we go along. So let's look at the first step. The first step is to create a table for each entity in the conceptual model. So the conceptual model is the one we created in the conceptual model lecture, this one. Now we should create our logical and slightly physical model. And okay, so I'm again using ASTA. But I've also created the same model in Lucidchart, and so you'll find both the ASTA model we are creating here and the Lucidchart model, the same model in Lucidchart, will be on the course web. Right, but now I've created an ASTA project, and I've created an ER diagram called VisitDB. We are modeling the visit database where patients visits doctors. So pause the video and do the first step to create a table for here in this model in ASTA. Create a table for each entity in this model here. Okay, now try to do that. Okay, that was perhaps not the hardest part of this procedure. I have created the tables here. So just simply each entity was transformed into one table. So we have the same tables as entities. Okay, that was perhaps not very hard. Still, we have not had to start thinking about which tables will actually exist in the database. This is just our first attempt at table candidates, we could say. Okay, but let's move on to the next step, which is to create a column for each attribute with at most one value. That is, attributes that have cardinality 0 to 1 or 1 to 1. So that is also not maybe not extremely difficult. We can see, for example, that in the description, sorry, what did I say? In the visit purpose table, there is one attribute called description. So we should create that attribute in the model. So visit purpose. By the way, the naming convention. So note the naming convention to use only lowercase letters and have an underscore between each word. So follow that naming convention. Right, so now it was time for the first column in visit purpose, which was called description, like this. And we still do not care about uniqueness or primary keys or not null or column types or anything like that. So we just create them, just write the names of each column now. But remember to only add the names for columns with cardinality 0, 1 or 1, 1. Okay, so now again pause the video and add all those columns. Okay, that was perhaps also not very hard. I have created one column here for each attribute in the conceptual model. The only thing that was a bit special here is that there were two attributes with higher cardinality. A person can have any number of both phone and email. So we shouldn't create columns for attributes with higher cardinality than 0, 1 or 1, 1. So there's no email or phone in the person table. Right, so that was that step, and we move on to step number 3. So that is to create a new table for each column with a higher cardinality. Well, I already said there were two such columns, phone and email. So let's right away create tables for those. Let's just call them phone and email. Phone and email. There. Okay, so that was the third step. And then the fourth step is a bit more tricky, to specify the type for each column. Okay, before we start to specify type for the columns, there are a few things we have to discuss. First, it would be a good idea to not just specify a type, but a domain. So domain means that we can restrict the legal values. For example, there is the zip code and the person number, which have requirements on format. and we could do that by creating domains. But that is outside this lecture, so we won't be creating any domains, but restrict ourselves to the basic types for now. Okay, but there are a few things we need to discuss related to types as well. So first, let's consider text. For example, first name, just to pick something, is obviously a text. So there are basically, as you know, three types for storing text: char, var, char, and text. So char is fixed length string. It will always have the same length. It will be padded with blanks. Var-char, this is an R. Var-char. So var-char are variable length strings. They will just contain the number of characters that are actually inserted, and we can specify a maximum number of characters. Var-char 50, for example, means that the database will check that not more than 50 characters are inserted. But if we insert 10 characters, the string will only be 10 characters long, whereas char always have the specified length. So char 50 means the string will always have the length 50 characters, and the text is like var-char without any limits. So a string that only contains that it is as long as the text that is inserted, but there's no limit on the amount of characters that can be inserted. Okay, so which one to choose of these for strings, like for example the first name? So here we come to a situation where when that depends on DBMS, and I have already decided that I will be using Postgres here. And for Postgres, the situation is a bit special in the sense that there's no performance impact. As far as performance concerned, we can take any of these types. Whereas for other DBMSs, like for example MySQL, the fixed length is faster. So if we were using, for example, MySQL, it would have a performance impact. We would make a performance gain if we choose char, for example, which is fixed length. But now we have decided to use Postgres here. Okay, and for Postgres, they all have the same performance. So that means there's really no point in choosing char. No reason to use a fixed length and then just pad with spaces. We can have a variable length text. So that means we have the choice between text and var-char. And the advantage of text is, of course, that we don't have to bother about the max length. Whatever we store there, it fits. And the disadvantage of text is the same. I mean, it's good. We should always have checks on everything, right? Always put some limit on anything. Do not allow the user to insert whatever. If, for example, the first name was a text, then a malicious user could insert a first name that was 2 gigabytes long or whatever. An argument against that, arguing still in the favor of text, would be that first, such checks, not to avoid unlimited length of a first name, for example, could be done in the application where the user enters their first name. Also, we could put column constraints limiting the length of the text. We'll talk a bit about column constraints later on. It's one of the coming remaining steps in creating this model. Okay, so we can restrict the text both in the application, we can restrict the string length both in the application and in the database, also if we use text. There are some subtle differences when it comes to indexing such things, which speaks in the favor of var-char. On the other hand, it's if we specify a limit that is too low in varchar, it can be quite hard to change that limit in a running database. Okay, so most things point towards text, one could say, even though there are advantages of using varchar. And I will actually choose varchar here, even though a lot talks in favor of text. And the reason for choosing varchar is that, as I said previously, which common practice and common sense maybe, that you should put some limit on everything. Should not allow a 2 GB first name. And I think that should not be deferred to the application. Such checks should be made in the application, but they should also be made in the database itself. The database should not rely on the application programmer. And since we will not introduce a lot of column constraints, for example, we will not talk about column constraints concerning string length here, then we use varchar instead. But we can choose reasonably high numbers, so we don't run the risk of having to increase the number later. Okay, so therefore, not text, but the choice is varchar, and try to keep high numbers, high max length, that is. So that was the first issue to discuss. Another issue we have to discuss is what to do with things that seem like numbers. For example, person number, and oh, now I realize we have not added columns in phone and email. So phone should have one column called phone, of course, and email should have a column called email. We can add those later. Let's make just a note here, so we remember email and phone. Okay, so what about, for example, phone and the person number? It might seem like a good idea to store those as numbers, using, for example, the integer, the 4-byte integer, or big int, 8-byte integer. But that is generally a bad idea. We should not use numeric times for things that are not really numeric. So the person number, for example, is an identifier rather than a number. And it happens to be an identifier which can only contain digits, but it's still more an identifier of a person than a number. You generally don't add person numbers or things like that. And it's, as I was saying previously, it's a bad idea to use numbers for things that are not truly numbers. For the person number, for example, what would happen if it started with a 0, like a person that's born 1909, for example? How to keep the initial 0 in a number. Okay, against this you can argue we always put decade. There's no 09 year, it's always 1909. But then we are just digging ourselves deeper into assumptions regarding formats and format constraints. There's no point in doing such considerations at all, but instead it's simpler to just keep identifiers as strings. So we will be using varchar also for person and phone, even though they all only contain digits. Right, and finally there's one more thing, the time column in the visit table should of course be some kind of timestamp. But do we need dates or not? Do we need time zone or what? Okay, we don't know. That would have to be discussed with the customer. For now, let's just decide to use the type timestamp, which is date and time zone. Okay, if you wish to use something else, that's of course fine. We don't know the customer's requirements. Right, so now let's start to add column types. And remember, we decided to use varchar for text, and we decided not to use integer types for person number and phone. and we have decided to use timestamp. At least I have. If you decide something else, that's fine. Timestamp for the time. And we should also add the email and phone columns. Remember to add those as well in those tables. Of course, if you wish to choose something else than varchar, another text type, fine. I will be choosing varchar and try to keep the max length reasonably high. Right. But before starting to add column types, we must know how to actually do it. So let's take description here as an example. So you can see that it's down here that the column type is specified. But you can also see up here that it doesn't show, right? There's no column type written here. Okay, but that can be fixed, and we can fix that by going to Tools and the System Properties and check ER diagram here. And then we have to specify properties here, what is visible. So in this case it's type and length, but now that anyway we are starting to define actual physical database things, let's just check all of them at once, and also check this one here, apply to the current project, and we click OK, and as can be seen, nothing changes. And that is because ASTA does not change entities that are already in the diagram, only new entities that are added. But it's not as bad as it sounds, because if we, for example, delete this one here, not using Control D to delete it completely from ASTA, but just delete button to delete it from the diagram, and then re-add it, so it's down here, and if we add it again, now as you can see, the column type is specified here. So while we're talking about ASTA configuration, there's one more thing I would like to mention, and also say that this part of this particular configuration, I'm recording this video afterwards, after the rest of the lecture. So I'm not using it in the rest of the lecture because I didn't know about this when I recorded that one, but now you will know now. Okay, and this thing I want to show you now is how to add new types to ASTA. So it can be done also here under Tools menu and ER diagram and set ER data type. And here we can add a new type. If we want to give a column a certain type and that type doesn't exist in ASTA, then we can add it here. And one typical case is for primary keys, which I will show here. So we haven't talked about primary keys yet in the lecture, but it will be explained later here. Right, and this type that is often used for primary keys is int, but with a condition, generated always as identity. Okay, close, and now here's the primary key, and now we can use this type here. So that's a way to add a new type. And what does it mean? I won't explain that here. It's explained in this text here. And in fact, it's also explained under project and task 2. And in this document here, I have also written a bit about this generated always as identity. But the purpose here was not to explain the meaning of that, but to show how you can add a new type to ASTA, and this was how to add a new type. Okay, so pause the video and specify column types. Before starting to look at each column type, there are basically, you could add different approaches here. In the Lucid chart model that you can also find on the course web, I've tried to be a bit smart and reason about a reasonable length of varchar, a reasonable max length of strings, what to use as constraint for varchar strings. Here in this model, I've not tried to be smart, but I just added a big number, 500, for almost all strings. Okay, the reasoning here is as developers, software developers, we should never try to guess the customer's requirements or the user's behavior, right? I mean, we should take all situations into account rather than guessing what the user will do or the customer will require. I mean, we could, for example, try to be smart and say no one has a first name that's 500 characters long. Why on earth should they? Maybe that's true. Probably that's true. But being dumb with requirement in regard of user behavior and customer requirements, we can say, well, a varchar column does not contain more characters than what is actually entered. So let's write 500. We could even have written 2000 or whatever, but let's just specify a number that is higher than the reasonable highest number that could be the reasonable max length. So 500 should, with good margin, be longer than any first name anyone can come up with, while retaining some reasonable security constraint. I mean, we shouldn't allow a 2 GB first name, but 500 shouldn't have an impact. Okay, we could argue reason more about that. Right, but that's two different approaches, and so you can see one where I try to think more in the Lucid-Chart model in the course web, and one where I thought less here. One can argue in favor of both. Okay, so let's look at the types. So for visit purpose, of course, this should be discussed with the customer also. But the problem that a person should be described in 2000 characters. You're not allowed to enter more. The time is timestamp, as I said. The employment ID. Here in this model, I'm not trying to be smart, so I just wrote 500. In the other version, in the Lucid-Chart version that I've uploaded to the course web, I wrote 10 here. And the reasoning was there that why 10? Well, I assumed the customer said an employment ID has 10 characters, or maybe they said an employment ID has 8 characters, and we took 2 as a margin if they prolonged them. Okay, but here I'm not thinking. Maybe at some time in the future, this organization completely changes the way they write employment IDs, and they become notably longer. Person number, okay, here I actually was thinking. A person number is max 12 digits, assuming we omit the dash. So I just wrote 12 there. I guess it will not change. But what do we know? Okay, the first name 500, last name 500, the ID of the healthcare establishment 500, street 500, SIP 500. Okay, this was maybe a bit too on the non-thinking side. I mean, a SIP is 5 digits long, right? Isn't it? Okay, city 500, phone 500, email 500. So the as I said, the foundation for these types was not to think. But I'm not saying it's wrong to think and put lower numbers. Your decision, simply speaking. Okay, but those were the column types. So we are done with step number 4, and we move to step number 5, which is to consider column constraints. We won't consider many types of column constraints here. We'll just consider 2 types, namely unique and not null. So unique means that it must be unique. No 2 rows in this table must have the same value for that column. And not null means that the cardinality is starts with 1 to 1, because we have no higher cardinality, right? We don't have 1 to any higher number. We created new tables for those. Okay, but not null means that we have 1 cardinality. Not if we allow nulls, then we have 0 1, but if we specify not null, that's not allowed. Okay, so we only consider these two types of column constraints. We can there are other ways to add much more specific column constraints, but I won't cover that in this lecture. I make a note here in the model before I upload it to the course, saying where you can read more about column constraints, other column constraints, if you're interested. But for now, we only consider these two, unique and not null. Right, so how to indicate that something is unique or not null. So first, not null. Now I'm not saying that description should be not null. I'm just taking as an example to show how to indicate not null. So not null you indicate here by checking this box, and then you can see it appears over here, not null. And right, so that was not null. And for unique, there's no way to indicate uniqueness. One might be tempted to use the primary key thing, but it can be unique even if it's not the primary key, so it's really not a good idea to use primary key to indicate uniqueness. So there is no way in ASTA to indicate that a column should be unique. Instead, we have to make a note, for example, like this, and write that something is unique, and then we attach it to the column that should be unique, like this, or we can instead just write beside the name, unique, like this. So those are the options. Right, so now pause the video and try to decide which columns should be not null and which should be unique. Okay, so then let's consider unique and not null, and this is what I came up with. And as you can see, I decided to draw nodes for unique. So, of course, many of these are things that should be discussed with the customer. We should never just guess the customer's requirements, right? But should always ask. But there is no customer, so I've decided on my own. Okay, let's go through them. First of all, we have 3 tables which all have just one column. And I mean, if we have a single column table and that column is null, then that's an empty row, right? So that's why I wrote not null on all those. I decided to make phone number and email unique. No point really in having the same phone number twice, and the same for email. So those should be unique. If 2 persons have the same phone number or the same email, we just add references, relations to both those persons. But then what about the visit purpose? That I did not put unique there, so no unique here at the description of the visit. So my thinking is that here this is free text. Someone working at the healthcare establishment, or maybe the patient themselves, write the description of why the visit takes place, and it's free text, so we just store it. I mean, if 2 persons write headache, they both see there are 2 different visits with the reason headache. 2 persons, or the same person at 2 occasions, had headache, and we don't like go through the table to see if there already exists a headache line. It's free text, so there might be duplicates. Okay, we can argue that it's not normalized if we have 2 rows with the same text. Maybe. I'm no fan of extreme normalization. I think we should not be afraid of this situation. I mean, following that line of reasoning, we could argue, what if there are 2 persons who both have the name Leif? Then we should we create a new table then with the first name, just the first name, and have Leif there? No, that's not meaningful. We should not go to that length of normalization. Okay, so that was visit purpose. Both no, not both, but yeah, both the doctor's employment ID and the healthcare establishment ID are not null. I mean, we don't. If we hire a doctor, that doctor is immediately assigned an employment ID, and each doctor should have their own unique ID. And the same for healthcare establishment. If we build a new healthcare establishment, we immediately assign it an ID, and that ID should be unique. Also, the person number should be unique. There are no two persons with the same person number, but why not null here for person number? Okay, here I try to reason as if I had been the customer ordering this system, and I was thinking that if someone arrives emergently and is dying, of course that person gets help even if we don't know their person number. So it might be the case that we are treating a person even though we don't know their person number, and that's why it's not null there. But that of course should be discussed with the customer. And I was thinking like trying to think like the customer also when I decided that we can have visits without time. Okay, I don't know why, but just assuming that it should not be the case. I was thinking that we refused a visit because we don't know when it took place. Okay, those are things that should be discussed with the customer. Right, so then this is my suggestion. If you came up with something else, that might very well also be fine. Right, so that was all about column constraints, at least as far as unique and not null goes. And as I said, I'll add a note here before I upload it to the course web where I put the link to someplace where you can read more about column constraints.